Hello and welcome back. Today I will continue with rock properties. To understand what happens in multi-phase systems, we need to consider forces that act on phase interfaces. Besides reservoir properties, which we have already discussed, there are some more very important ones. We start with saturation. It is commonly believed that oil-saturated and gas-saturated formations were initially saturated with water. As petroleum deposits were formed, oil and gas, due to their lower density, migrated up through formations, pushing the water out. What happened is that they did not push out all of it. So even an oil-saturated formation contains some so-called residual water. The smaller the pores and lower the permeability, the more residual water remained in place. This water occurs as a thin film of water molecules on pore walls, or as connate water in isolated pores. For our purposes, we are interested in residual water contained in open pore space. Oil saturation factor or gas saturation factor is a ratio of oil or gas volume contained in open pore space to the total volume of the open pore space. Similarly, water saturation factor is the ratio of water volume in open pore space to the total volume of that space. These parameters are related in the following ways: for oil-saturated reservoir, for gas-saturated reservoir. For gas-saturated reservoir contains residual oil besides residual water. It is very important to study water saturation, not only because it helps us to estimate how much oil is contained in the reservoir. Residual water in pore space has great influence on hydrocarbon displacement from pore space during field development. One more property is rock compressibility. It may be of three types: matrix compressibility, bulk compressibility, compressibility of total or bulk rock volume, and pore volume compressibility. The first two compressibilities are negligible compared to the third one. Pore volume compressibility is the change in pore volume of rock in response to change in pressure. It is quite natural that as reservoir pressure drops and external overburden pressure remains the same, pore volume decreases. This happens because rock grains regrow and expand, reducing pore space. Rock compressibility is determined in laboratory or through empirical correlations. Pore volume compressibility is a tricky thing. On the one hand, it helps extract more hydrocarbons out of the reservoir. Yet, on the other hand, it can cause severe environmental problems. You might have heard of the famous Ekofisk offshore field. The rock compressibility caused next to catastrophic subsidence of the seafloor. 6 oil platforms became insecure and the company had to jack them up by about 6 meters. This operation cost about $400 million. Another important factor is surface tension. This tension emerges on the interface boundary between two immiscible fluids such as water and oil or oil and gas. If you look at a drop of oil, we can see that it wants to take a shape with a minimum surface area. Should we want to change the shape of the drop, we will have to apply a certain force. Another good example is a soap bubble. Any liquid at all has a kind of thin but firm film that covers its surface. Thanks to this film, a soap bubble takes a shape, while soap added to water makes the film stronger. It is very important to remember surface tension forces while planning haste or recovery operations. As we apply the so-called surfactants, surface active chemicals, we reduce surface tension down to extremely low values, thus producing more oil. Surface tension explains such phenomena as wettability, adsorption, and capillary effects. Let us start with wettability. Wettability is defined as the tendency of one fluid to spread on or adhere to a solid surface in the presence of another immiscible fluid. Thus, if you put two fluids onto a solid surface, the one that gets more attracted to the solid than the other will occupy the largest area. Suppose that fluid A is more attracted to the solid than fluid B. With time, fluid A will occupy a larger area than fluid B. The value of wettability is expressed through the contact angle theta, which is always measured within the liquid phase. If the contact angle tends to 0, then fluid A is the wetting phase. If the contact angle varies from 60 to 90 degrees, we have mixed wettability. If the contact angle tends to 180 degrees, then fluid B is the wetting phase. Rock wettability is very important for fluid distribution in the pore space, as by definition the wetting phase will tend to occupy smaller pores, while the non-wetting phase will occupy larger ones. Now, on to capillary pressure. Capillary pressure is determined as a pressure difference on the boundary between two miscible fluids. If you know the wettability of the system, we can describe capillary pressure as the pressure difference between the wetting and non-wetting phase. Thus, for the oil-water system, then the rock is water-wet, we can express capillary pressure the following way. Imagine a vessel filled with oil and water. It has a certain radius. We take a tube on a smaller radius and lower it into the vessel. If a tube is made of water-wet material, capillary pressure will cause the water to rise to a certain level inside the tube. Capillary pressure can be also expressed using the following two equations. Based on the equation, we can see that the capillary pressure is inversely proportional to the tube radius. Now back to the oil field. Pay attention. This will be in the test. If the imagined reservoir rock as a system of tubes varying in radius, we conclude that the water will rise to a high level in smaller pores, and capillary pressure in such pores will be the highest. Capillary forces manifest themselves in a similar way on boundaries between oil and water. To move oil at oil-water contact, we will need to create a pressure difference that will exceed the capillary forces. Putting it simple, if we use a wrong method to push oil out of the reservoir, it may remain caught in larger pores, and it will be extremely hard to extract this oil. Let's study typical capillary pressure curves. They describe two fundamental processes that happen in reservoir: drainage and imbibition. Drainage happens when we displace a wetting phase, that is water, with a non-wetting phase, that is oil. Imbibition is a reverse process. We displace a non-wetting phase with a wetting one. This is what happens during the recovery method called water flooding. We displace oil with water. Pressure, PD, is the initial displacement pressure that I mentioned earlier. Note that a reducible water saturation capillary pressure tends to infinity. Thus, let me repeat, if you want water to displace oil efficiently, we need to create a certain pressure. And the final example, oil-water or gas-water contact is a minimum depth at which we observe a 100% water saturation. There is another parameter called free water level, the depth at which we observe 100% water saturation and zero capillary pressure. Above this level lies the so-called transition zone. Their water saturation changes from 100% at oil-water or gas-water contact to the minimum water equal to connate water saturation. From what we have learned, we can infer that transition zone in low permeability reservoirs will be significantly larger than in high permeability rocks. This is all I want to tell you about rock properties. Next time I will tell you about oil and gas properties. See you!